All right, heating and cooling curves, what are they? They're basically representations of a state change as a substance goes from a solid, liquid to gas. In the case of a heating curve, you put energy in, what happens to the states, what happens to the substance. And as you go cool the substance from a gas to a liquid to a solid, which is called a cooling curve, it shows you how the states change in that direction as well. So that's basically the point of it, to show you how energy and time impacts a substance as you go from one state to the other. So what are some things that happen as we heat a sample up? Well, if you look at this cup with ice, as you increase the temperature, the ice is going to melt. So you can go from solid to liquid. As you keep on adding temperature or energy, you make the molecules move even faster. So now they're going from liquid, and then eventually you could break the interaction between two H2O molecules and cause them to go into gaseous phase. So solid, remember, they're tightly packed together. You put energy in, you weaken that interaction a little bit, so they're able to move a little bit, become a liquid. Put more energy in, they're basically able to break off from each other molecule-wise and become a gas. So that's what occurs in more or less. You go from solid, liquid to gas. And it's basically based on the movement of particles and energy put in. So what is heat? To give you a review, heat is basically a transfer of energy, right? You can calculate using Q equals MC triangle T. That's the normal way. And all it basically does is tell you if energy is going into a system or out of a system. That's the whole point of heat. Temperature, on the other hand, measures how fast the molecules are moving, whether it's the gaseous molecules around us, whether it's talking about the liquid molecules, how fast is their motion. The faster their motion, the higher the temperature. So how does a heating curve look? This is a heating curve. So let's look over the components. So this is water, obviously, because you have 0 degrees Celsius as the melting point. So first thing, we have a solid. The diagonal lines represent single states. So this is a solid. And as you increase temperature, what happens? Well, the solid starts melting, right? And that occurs at 0 degrees Celsius. So at that point, we have solid and we have liquid. We have both states together. Now, why both together? Because at 0 degrees, both states can exist simultaneously. As you keep on putting energy in over time, eventually you get to the point now where all the solid is gone. So if all the solid is gone, the energy you're putting in is no longer being used to melt the solid. It's going to be used to increase temperature. So that's why the temperature spikes. Temperature spikes are usually associated with single states. So this is solid. This is a temperature spike. Like this was a temperature spike too, right? So this is going to be a liquid, single state. So diagonals are single states. So you have to remember that. And as you keep on putting energy in, you eventually get to the point where now you have liquid, and you have some of the liquid becoming gas. At what temperature? 100. Remember, water boils at 100 and freezes at 0, or melts at 0 too, right? So as you put energy in, the liquid and the gas start moving faster and faster, and the molecules do. Then eventually you get to this point right here where all the liquid is gone. Now you have nothing but gas. So what happens at that point? The temperature spikes again. So what do you need to know about this graph besides the states that exist in each point? The kinetic energy. So at the horizontal lines, the kinetic energy is 0. There is no change in kinetic energy, right? There's no change in it. Same thing with here. Kinetic energy is constant, so it's not changing, so it's considered more or less 0. So when is kinetic energy changing? At the diagonal lines. So here, kinetic energy is changing, here is changing, and here is changing. If you remember, kinetic energy and temperature are basically proportional or related, right? As you increase temperature, you increase kinetic energy. As you lower kinetic energy. So that's why kinetic energy is increasing at those given points. So those are the components you need to know. The other thing you may want to consider is that this is called the heat of fusion. This is the energy you'll need in order to melt something. Fusion is a fancy way of saying melting. Why they use fusion to indicate melting, who knows? And this is going to be called the heat of vaporization. Vaporization, that makes a little more sense. You're going to vapor states, so you're basically going to a gas. So these horizontal lines are also known as your heat of fusion. For here, this is where melting occurs, so that's a state change. And here is where boiling occurs. Now, I do want to make something clear. Not only does melting occur at 0 degrees Celsius here, but also freezing. Both states exist simultaneously. So you have freezing and melting exactly at 0. So it's important to remember that. And vaporization or boiling also has condensation also occur at the same temperature. So not only at 100 degrees you get liquid going to gas, but you also have gas going to liquid. So both exist simultaneously. So the flat points, as I mentioned, is because you have single states, and that's because the kinetic energy is staying constant, and all the energy you're putting in is being used to make that substance stay as is. All right, so different components: heat of fusion, heat of vaporization, what we talked about a little earlier. So what is the heat of fusion and what is the heat of vaporization? HF is just basic energy you need to make a solid turn to liquid. So fusion is just code word for melting. That's all you got to really remember. HV is the amount of energy you need to make substances go from liquid to gas. So basically your boiling point. The energy you need to make something boil. That's all it is. It's just semantics using fancy words to describe simple processes. All right, so let's try some questions. Water condensed at a temperature of, now remember, condensation and boiling occur at the same temperature. And for water, you should remember that it's 100 degrees Celsius. That's an important temperature to recall. So that's going to be 100 degrees Celsius for number one. At temperature of degrees Celsius, water does what? Freezes, melts, changes to gas. Remember, two things occur simultaneously. Not only does melting occur, which is what you usually would think, but also freezing. When a gas condenses, heat is, well, condensation is going from a gas to a liquid, right? You're losing energy. You're moving less. So that's going to mean heat is released. Whenever you lose, remember, exothermic is losing. So whenever you lose energy, it's going to be exothermic. Freezing is, once again, you're losing energy. So it's going to be exothermic as well. And that is heating and cooling curves in a nutshell.